Okay, so we are now in lecture number 2. This is on September 2nd for Math 140 Science. Can someone send the link? Which link are we talking about? I'm not sure what link that is. What's a Discord? Or group me for here. I don't know. Okay, you guys are saying English, but it's like not English at the same time. I don't know what's going on. So can we all see this here?
Yeah.
Okay, so here we have a group of data. Percent of state high school students graduating on time. And we have this table where we actually have many different individuals. In fact, how many individuals do we have in this? How many individual? What's all this link, please? For what? Do I have a link that I'm supposed to be sharing, or is it something else? I'm not sure what people are saying.
I don't think it's for you. I think it's like
Okay.
Yeah.
Okay, so how many individuals do we have in this data set? This is the percent of high school students graduating on time. And it looks like the individuals would be the different states.
Would it be 50?
Well, you would think so, wouldn't you? But look closer at the table. What do you see? I see District of Columbia, which is not a state per se, but they're including it. So there's actually 51 individuals. I don't see Puerto Rico or any of the other various, I don't even know what they're called. I'm not really a history, sociology type person, but what are they called? Parts of America that aren't part of the states. Anyone know what they're called?
Territories.
Territories, maybe yeah, that sounds familiar, territories. But anyways, we have 51 individuals. And of these 51 individuals, how many variables do we have for each one? According to this table, how many variables do we have? Just 2. And the first variable as listed, is that quantitative or is that categorical?
Categorical.
Which one's categorical of the 2?
The state.
Well, the states are the individuals. So that's not a variable. Those are the actual things that we're looking at one at a time. The variables are the features regarding those individuals. So yes, the region would be a categorical variable, right? Some individuals are in the South. Some individuals are in the West. Some are here, some are there, and so on. Right? Does that make sense? Whoever it was who guessed states?
Yeah.
Okay, and the other one is the percent. And is that quantitative or is that categorical?
Quantitative.
That's quantitative. So they went ahead and they grouped them into classes, 70 to 72.5, 72.5 to 75, and so on. And then they went ahead and they drew a histogram. Now, if we want to analyze this histogram or interpret this histogram, which is section 1.4, there are essentially 4 things that we were looking for. So section 1.4 on interpreting histograms, there are 4 things that we look for when we look at a histogram. I'm running this down on the iPad, which I'll share in just a minute, but I want you to see the histogram, and then I will stop sharing on my computer and share on the iPad so you can see what I'm writing. The first one is called the shape. We're looking for an overall approximate shape of the histogram, and there's essentially 3 possibilities in this class. The first possibility for the shape we would say is symmetric. And what symmetric means is if you look right in the center, it's pretty much a mirror image on both sides. So a symmetric graph would be something like just a nice, hump, like what we call a bell curve. Does this particular histogram look symmetric?
No.
No. Okay, certainly if you look in the middle, it's not a mirror image on both sides. If it's not symmetric, for this class, we call it skewed. And there's two possible ways it can be skewed. It can be skewed to the left, or it can be skewed to the right. We're not going to have any other possible value for shape besides symmetric, skewed left, and skewed right. And to determine if it's skewed left or skewed right, we look at the tail. Whichever side the long tail is on, it's skewed that way. So for this particular example, is it skewed left or is it skewed right?
Skewed left.
Skewed right.
Skewed left. The tail is on the left, isn't it? I know I heard one person say left, which was correct, but I heard someone else say right.
What do you mean by
That's
tail?
not bad.
What I mean by tail is
The shorter part that goes out long?
so that's kind of like what the shape looks like, right? So if I were to ignore this part, it would look kind of symmetric. It's this that's creating the skewness. The tail side is what creates the skewness. So whichever side the long, low tail is on, that's the side of skew. There's a mathematical formula for calculating skewness, which we're not going to use. Ours is going to be a purely qualitative answer to this question. What is the shape? Is it symmetric approximately? Is it skewed left or is it skewed right? In this example, it's skewed to the left. The next of the four characteristics of a histogram that we might be curious about is where the center is located. The center is basically an average, but there's multiple types of averages. There's three famous types of averages. Anyone know the three famous types of averages? What are the three famous ones?
Mean, median.
Mean, median,
Mode.
mode. Mean, median, and mode. Now we're going to get to each of those three later. We're not worrying about them now. For now, here is how I want you to think about the center. If you were to build a physical object in the shape of the histogram, and you would put it, let's say, on your palm. So it's like, like this, up here and low here. You'd be able to hold it, no problem. Life goes on. Everyone's happy. If I asked you to balance it on one finger, where would you place your finger underneath the histogram so that it does not tip either way? If you were to take a guess, I'll give you a few possibilities. Would you put your finger right here and expect it not to tip?
No.
No, I mean, that's ludicrous, right? That's certainly it's going to tip to the right. How about here? What do you expect here?
It's still gonna tip more towards the right.
Oh yeah, look how heavy it is to the right compared to the left. Let's say you go to the peak. How about here?
No.
Which way would it tip now?
The left.
To the left. How about something in the vicinity of there? So wherever the balance point is, that's the center. So on my iPad, I'm just writing for center balance point. I'm not really putting an explanation there, but I'm calling the center the balance point. Okay, that, by the way, when it comes time to calculate averages, is called the mean. It's a physical interpretation of the mean as the physical balance point. The next of the four features of a histogram that we're going to care about is called the spread. So we have shape, we have center, and we have spread. Spread is essentially lowest to highest. In our case, the spread of this histogram is 70 to 92.5. You're just giving the lower to the upper. It's spread out from here to here. That is the spread, which, by the way, is a horrible feature to use to describe a histogram because it says nothing about where the data is concentrated. You know, if there's a tail on the left or a tail on the right, the spread is not going to tell me one way or the other. And the last one, the fourth feature, are outliers. Are there any points? Are there any bars of data in this histogram that are far outside the norm? Do we have like an extra column here that is just way outside the rest? In our case, there are none. And we're going to have a numerical way of determining whether something's an outlier or not. But for now, if I stop sharing here and start sharing here, only the host can share, so okay. So this is what I have. Right, so you have shape, symmetric, skewed left, or skewed right. Center is the balance point location, I guess we can say, I don't know. Spread, I'll just say low to high, lowest to highest. And for outliers, are there any data points outside the norm? Something like that. It's not very specific, which is why I use quotation marks for it. It's more of a general perception. You're not going to be given any questions where the answer to that question is hard to decipher, where one person might say one way and someone else might say the other way, and both of you are correct. So, okay, it'll be obvious, or should be obvious. Okay, so are there any questions on that particular concept of interpreting histograms?
No.
Okay, so a histogram is one of the two ways of describing a quantitative variable. The other display of a quantitative variable is does anyone know, without looking in the book, what the other display for a quantitative variable is? We have a categorical variable. Is there a second one? We know pie charts and bar graphs are fantastic for categorical. And now the question is, what about quantitative? We have a histogram, but the question is there anything else?
A stem plot.
So the other one is a stem, oftentimes called a stem and leaf plot. The book calls it just a stem plot, but back when I was learning this years and years and years ago, we called it a stem and leaf plot, but it's essentially the same thing. It is the same thing, just two different names for the same thing. A box plot is a good answer, by the way. Box plot is correct, but we're not ready for box plots yet. We have to learn about a few other things before we can use those. But yes, the box plot is 100% a great way of displaying quantitative data. We're just not ready for it yet. So what is a stem plot? That's a great question. I'm glad you asked. So it's really nothing beats Sing It in action. So I'm going to go back here. Okay. So we finished this section and okay, stem plots. Okay. So essentially here's the idea. So here is a collection of data. And if you don't know what a stem plot is, and you're looking at this, it can be very confusing. Essentially what's happening here is on the left of the vertical line, you have what is called the stem. And on the right are the leaves. Every stem can have multiple leaves attached to it. So there's 8, 8, and 9 are attached to the 0. And 1, 5, 5, 6, 7, 8, and 9 are attached to the 1, and so on. And each of these leaves is one data point. So how many data points are there in the first row? There are 3. The 8, the 8, and the 9. How many data points are there in the second row? There are 7. So what do these numbers and this number here represents? So the first thing you need to know is the context. The stem, they're telling us right underneath, the stem is the tens place. So the stem is the tens place. This is a tens place. And the leaf are the ones place or the unit place. So the first data point is 0 tens and 8 ones. What number corresponds to that? 8. The next one is the same stem, but this time the next leaf. What number corresponds to that? That's another 8. We have 2 8s. The next is the same stem, but the next leaf. What number corresponds to that? 9. So the first row has 3 data points, 8, 8, and 9. What would be the next data point?
11.
11, followed by
15.
15, then 15, then 16, 17, 18, 19, 20, 22, 23, and so on. So again, the stem attaches to each leaf, and each leaf is 1 data point. Now, who here can see an immediate advantage of using the stem and leaf plot instead of a histogram? What do we lose in a histogram that we do not lose in a stem and leaf plot?
A specific center.
And what do you mean a specific center?
Like the value of the center. Like you would know where the...
Well, you can certainly calculate it with a stem and leaf plot, and you can't with a histogram. That's true. And that is an answer to my question. You're right. For a histogram, we lose the ability to find the exact center, whereas for a stem plot, we still can. But it's even more fundamental than that. For a histogram, you lose all of your data. I don't know any of my data points for a histogram. I know which block they fall in. 7 fall in here, 19 fall in here, 12 fall in here, and so on. I know where they're located, but I don't know any specific data points at all for a histogram. I lose all of that. And of course, losing all of that, I can't compute anything. So your answer is correct. I cannot compute the center. But it's worse. I don't have any data points. So what you have for a stem and leaf plot is kind of like a hybrid. You still have the columns, although they're turned sideways usually for a stem and leaf plot, but you don't lose any of your data. Does that make sense? Notice, yes. By the way, although we didn't have the situation here, but suppose there were no data points. Suppose none of these 3 were here. Just suppose, for example, there were no data points that had 60 anything. You would still, and this is important, you would still have to include the 6. You still write the 6, even if there's no data points. It's no different than a histogram where you have bars and there's no data somewhere. You don't just skip that region, right? That region is still on the x-axis. It's just there's no data there, so you have no column. So you skip a spot. You don't just move the bars next to each other and pretend it's not there. So it's the same thing for the stem and leaf plot. If there doesn't happen to be any data for one of your stems, you would still write the stem, and just there happens you wouldn't write anything for the leaves. Does that make sense? I mean, any questions on that? Does it seem reasonable?
Yeah, makes sense.
Okay, again, you have to stop me at any time if I say anything that does not seem reasonable. Now, there is one adaptation of a stem plot. What if I have a situation like this? So I create a situation, I have 3 stems, and I have lots of leaves on one of the stem, or possibly more than one stem. There's certainly nothing wrong with the stem and leaf plot, but perhaps I feel that just like with a histogram, you know how you can change the size of your classes, you can change the size of your bars. I would like to be able to do the same thing with the stem and leaf plot. Maybe I'd have a better grasp of how the data is distributed, which at the end of the day is the goal. So what I can do is I can do a split stem. I can say, I'm going to create 2 rows for the 7, 2 rows for the 8, and 2 rows for the 9, and divide the leaves between 0 to 4 and 5 to 9. 0 to 4 goes in the first, 5 to 9 in the second. And if I do that, I'd get something that looks like this. You can see here, 7, 1, 7, 3. That's my first row. 7, 7, 7, 8, 7, 8, 7, 8, 7, 9, 7, 9. Second row. It's more pronounced with the 8 that has lots of leaves up until 4. Those all go into this row. And with the other end of the 8, all the rest of them. And 9, I don't actually need to make the second row because just like a histogram, if you change the width of your last class and make it smaller and you still have all of your data, you wouldn't include that last bar, which has nothing anyways. So same thing here. If the outside stems or split stems don't contain any data, you don't have to write them. It doesn't, I mean, if I did it, it wouldn't change the shape of the distribution. Does that make sense? And actually think about it. If I asked you by looking at this stem plot, is it symmetric? Is it left skewed or is it right skewed? Approximately at least.
Symmetric.
It seems fairly symmetric. You got a big column in the middle, and then you got a little smaller column on either side that are roughly the same height. But when I do it like this, you see it's not as symmetric. If I had to pick a skewness, which would it be? Left skewed or right skewed?
Left.
It's a little bit left skewed because we kind of see that the peaks here and it kind of tails off more on the lower numbers, which when you tilt it sideways would be the left than on the right. So you kind of get a different perception of the shape depending on how you split your stem and leaf plot. Does that make sense? Again, these are just graphical displays. The majority of this semester has got nothing to do with this, but being able to display data is an essential part of statistics. It's just kind of boring because there's no calculations. There's no analyzing, there's no predicting, there's no testing. It's just here, have a little picture. Again, important, but not nearly as exciting as the rest. And just one last display. It's in the book, although it's not tested upon, but there is a third graphical display called a dot plot. A dot plot is very much like a histogram, but instead of bars indicating how high it is, you use actual dots to indicate the counts. So it's just a little bit easier to see or to count the frequencies in a dot plot versus a histogram, but it's really saying the same information. There's nothing different between a dot plot and a histogram. You still have your classes. You still have how many per class. Remember, a histogram, you can count frequency or you can count percentage. For a dot plot, you can only count frequency because you're actually counting how many, so you can't do a percentage. But other than that, they're exactly the same. Does that make sense? Questions? Seems fairly reasonable.
Yeah.
Okay, we're all happy, live lives of religious fulfillment and whatever makes us happy. Okay, the last section of chapter 1 is on time plots. Time plots are their own animal. we only do it for quantitative variables, but it's one individual looked at over and over and over again. A dot plot, a histogram, and a stem and leaf plot, each counts is a different individual. A time plot is the same individual measured at different points in time. So can anyone think, by the way, because I've seen these a lot out there in the world, what are some very popular time plots that you might have seen in either TV shows or movies or, you know, your own business life if you lean in that direction? What are some things that measure something over time? Let's see, I have a chat. Rainfall per year, 100%. That's kept, that people measure that. They'll say something like, this is the first year in the last century where we've had this many inches. How do they know that? Well, they've kept track. Otherwise, how do they know? They don't just guess. What else we got here? Hair growth. Let's not talk about that, okay? It's a very sensitive subject, and I just don't like that particular one, so I'm just going to ignore that. Can we talk about something else, please? But yes, I guess technically hair growth would be something. COVID cases. Yeah, that's a beautiful example, especially in today's climate, right? Are they going up? Are they going down? Love it. Let's see what else we got. Stocks, that's what I was thinking, right? People who really analyze stocks will look at individuals and when does stock prices go up and down? Oh, it's every Christmas, these things skyrockets and then it's over there. And so right before Christmas, I'm going to buy low, sell high, whatever I want to do. There's people who go crazy in that. That's not my thing, but I've certainly seen it. The most famous that I know is an electrocardiograph that measures, heart rate, boop, 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 that thing that we see all the time in, Grey's Anatomy and stuff, because, we all watch it, of course, great show. So these are all time plots. You're measuring something over time. It goes up, it goes down, and it does various things. Essentially, there's two things that you're really looking for time plots, and that is you're looking for cycles. You're looking for periods of time where it keeps repeating, especially for stocks. That would be a good thing to know when it goes up, when you expect it to go up or down. And you're looking for trends, overall trends in the long term. Are we on the way up, even slightly? Are we on the way down? Is it essentially the same? Like this graph here looks like the trend is pretty much, it cycles, but it seems fairly the same at its center throughout. These are things that you might care about if you were analyzing time plots. Does that make sense? Any questions on any of that? Okay, so that's the end of chapter 1. And when I look at the schedule for this class, essentially chapter 1 was the intent for the first week. So what we're going to do now is we are going to load up the workbook that is listed under files if you haven't downloaded it yet. And we are going to answer the questions that we skipped last time for chapter 1 because we hadn't covered them yet. So I'm going to load up here. And okay. So which one did we not do yet? I don't think we did. I don't think we did 17 was the first one. Is that correct? I believe 17 was the first question we didn't do yet. So 1.17. Okay. So it says figure 1.6 on page 25. I have it here. And they're showing it down there as well, it looks like, is a histogram of the percentage of on-time high school graduates in each state. The rightmost bar in the histogram covers percents of on-time high school students ranging from about 85 to 90%, 88 to 92%, or 90 to 92%. So I will give you 5 seconds to think about it. And then I want you to type in, when I say go, I want you to type in whether you think it's A, B, or C. I want to see, when I say go, I want to see a whole sudden scrolling of answers. Hopefully they're all correct. One, two, three, go. So I got some C's, I got some B's, I got some A's. I got a lot more C's, a lot more C's, a lot more C's. At this point, it's probably peer pressure, but I got a lot more C's. And the answer is C. And you can just tell just by looking at the rightmost column, which is right there. The left side is 90, the right is 92. If you said A or B, and there were a couple who did, maybe you're misunderstanding the question. So say something, explain, do something. I don't want to leave you behind, but that should be fairly immediate. So are there any remaining questions on why the answer is C for question number 17? Going once, going twice. Anyone? All right, well, I can't divine your questions, so hopefully whatever they were have been answered. So the answer is C. 1.18. Here are the exam scores of 10 students in a statistics class. To make a stem plot of these data, you would use stems, and then you have options A, B, or C. I would like you to think about that for a second. And then I will, again, say go. And when I do, hopefully I'll see a whole slew of correct answers. And possibly some wrong ones. Nothing wrong with wrong answers. It means we have something to learn. And that's really the best things possible. Okay, so A, B, or C, 1, 2, oh, someone already go. I didn't say go yet. Oh, now people are just running ahead. Jeez. Oh. See, it all it takes is one person, huh? That's all it takes. So let's take a look. We got A, B's. We got some B's, we got some C. Mostly, I think, B's and A's mostly. I don't even know where it started because I didn't say go. Oh, there it is, Andy. Oh, okay, I'm gonna keep an eye on you, Andy, jumping the gun there. But let's take a look. Mostly A's and B's with a C in there. So let's take a look. So the answer is certainly not A because of what? Why is the answer not A? There's one reason and one reason only. It's missing a place value. What is A missing?
It's missing the number 8.
It's missing the number 8. And that's enough to make it wrong. You don't skip place values. Now, why is C wrong?
Because if you had the second digit in the leaf part of the graph, it would be like 203.
Exactly, or 20.3 possibly. You have to describe the placeholders for each thing. But you're right. Assuming it's tens and ones and whatnot, it makes no sense because 200 something, we don't have any data point that starts 20. So it can't be C. Now I would say by process of elimination, it's B, but it's also B because B just happens to be correct. Does that make sense and why it should be B and why it can't be? I saw a lot of people write A. So I'm hoping that that clears up why A is incorrect. A lot of people wrote it, so I'd be very happy if at least one person says, yes, I got it now. Okay, okay, got it. Okay, got it, got it. Okay, good. All right, excellent. So now 1.19. Where do students go to school? My voice is hurting, so I'm going to let you guys read it. Although people watching this video might not have it, so I'll say it anyways. Okay. About 78% of first-time, first-year students attended college in the state in which they lived. But this percentage varies considerably over the states. Well, I'm curious, everyone in this class, is anyone here not a native of California? Native, I don't mean like born in California, but I mean living currently in California. Is anyone attending CSUN because they live in Massachusetts where they're like, oh, CSUN's a great school, I'm gonna go there across the country? Nobody. So everyone here lives in California.
I don't.
Where do you live?
I'm from the Big Island of Hawaii, and I come here for school, and then I go back home.
That's awesome.
Yeah.
I actually had a student a couple years ago from Hawaii as well. That's really nice. Okay, but most people, at least in this school, live in California. But if we were talking about UCLA or Berkeley or USC, so there's certainly other colleges where people would come significantly more so from out of state. So anyway, here's a STEM plot of the percentage of first-year students in each of the 50 states who were from the state where they enrolled. The stems are 10s and the leaves are 1s. And the stems have been split, which you can see because we have 3, 3, 4, 4, 5, 5, and so on. So the question is, what is the midpoint of this distribution? Well, that's so cool. Her coming from Hawaii or something I said? Or both? Or neither? I don't even know. Anyways, so what is the midpoint of this distribution? Is it A, 60%? Don't answer yet. Again, I'll say go. But is it A, 60%, B, 73.5%, or C, 80%? So I'm going to give you a couple seconds to think about it. And then we'll take our guess. Okay, I got my answer. So on your marks, get set, go. That's what I'm talking about. Yeah, everyone's right on target there. A, B, B, lots of A's, lots of B's, more B's, a few A's, mostly B's, lots and lots and lots of B's. Okay, so let's go back to the histogram. First, nobody said 80%, which is great. 80% is wrong. But there were a few people who said 60%. And that's also wrong, but I can understand it. The reason why I can understand a 60% is because it's right in the center. But that's not how we denote the center. W was not an option, Jason, I'm sorry. But that's not how we denote the center. The center is the balance point. If you put your finger at 60%, would it balance? If you tilted this sideways and you put your finger at 60, would it balance? Or would it tip more one way versus the other? And I hope you notice that it would tip to the right because there's significantly more data points on the right side. And same thing with 80%. If you put it at 80%, there's significant, not only are there more on the left, but it also goes very far to the left. Whereas 73.5 is at least somewhere in the vicinity of the balance point. Do we agree with that? So the answer is B, 73.5%. All right, 1.30. Do adolescent girls eat fruit? We all know that fruit is good for us. Actually, we don't. Various diets say it's really high in sugar. I personally don't believe in diets, but that's what I've heard. Anyways, many of us do not eat enough fruits, I assume. So figure 1.17 is a histogram of the number of servings of fruit per day claimed by 74 17-year-old girls in a study in Pennsylvania. Part A, describe the shape, center, and variability, i.e. spread, of this distribution. So go ahead and write down, not on the chat, but just on paper, write down what you think the shape, center, and spread of this data are. And then I will quickly ask for one at a time and hopefully get a whole string of correct answers. And there's not many to go. In fact, the next question is the last one after 30. We do 130 and 31, and then we're done with the chapter. So not a lot more to do today. Okay, so for the shape, there's three options. It's either symmetric, skewed left, or skewed right. You can either type in, don't hit enter yet, but you can either type in symmetric, left, or right. And if you write left, I will assume you meant skewed left. And if you write right, if you type right, I will assume you meant skewed right. So type in, but don't yet hit enter, symmetric, left, or right. And 5, 4, 3, 2, 1, go. So I see almost, I think everyone, no, I do see one person who said left, but I see almost everyone else said right. So it is to the right, because remember, the skewness comes from the tail. The long, low tail is on the right side. It is skewed to the right. So hopefully that clears up that one, but it is certainly skewed to the right. Do we agree with that? Yes, hopefully. Okay. Next, center. So type in a number. We're not all necessarily going to agree on the exact decimal, but hopefully we'll all be in the correct vicinity. Type in the number, but don't yet hit enter, of the point that you claim would be the center of this distribution. I'm going to pick what I think it is. Okay, I have a number in mind. Hopefully we'll all be in the vicinity of that. So 5, 4, 3, 2, 1, go. All right, so I have, yeah, so I personally picked 2.5 myself. I see lots of 2.5s. 3 is fine. 3.5, no. By the time you reach 3.5, I think it's clear by the time you reach 3.5 that the left side will certainly tip over from the right. Do we see that? If you put your finger at 3.5, it kind of goes the same distance in both directions, but it's certainly heavier on the left, right? Someone I think said 2, again, fairly close. Maybe you're even more correct, 2.4 I see. But yeah, certainly around 2.5. 3 would be a limit. Anything past 3, I would say no. Do we agree with that? Make sense? Okay, next we have the variability, i.e. the spread. This one should be, we should all agree on this one. So 5, 4, 3, 2, 1, go. Yeah, excellent. Yeah, 0 to 8, lowest to high, 0 to 8. Lovely. Everyone wrote that exactly. Love it, love it, love it. And then for part B, are there any outliers? This is a simple yes or no question. So just go ahead. Are there any outliers? The answer is straight up no. That's me. Everyone's, yeah. So I'm talking, nope. That's like an emphatic no. That's like awesome no. I love it. All right, part C. Now this one's a little more complicated. What percentage of these girls ate 6 or more servings per day? So I got to calculate this myself now. What percentage of these girls ate 6 or more servings per day? Okay, so I have my answer. I just came up with it. I'll give you a couple seconds. I'll even convert it to a decimal and then to a percentage as opposed to a fraction. So I have a fraction number here. Anyone need a couple more seconds to think about this one? Okay, so 5, 4, 3, 2, 1, go. Ooh. So first only 4 answered. Where's that huge scrolling of 35 to 40 people that I had a few minutes ago? And then I have 3 people wrote 12 or 12%, I assume. I have a 25, I have 62.6. I'm waiting for some more people. The same 5. Where is everyone at? Oh, we got another one, 12%. 4, 25. Good. Obviously we got some wrong answers here because they can't all be correct, which is great. But here's the thing. If you leave it blank, if you don't answer, and then you just see the answer later and you go, yeah, I would have written that. I mean, yeah, I would have gotten that one. You're robbing yourself of determining whether or not you truly would have gotten it correct. If you write it down and then you're wrong, you'll know that you were wrong. You won't just blindly say, I would have gotten that, because half the time we wouldn't have gotten that. So the question, 14.8, very specific, but no, the answer is about 12.16%. 12 points, actually, I think it's 12.1612 bar percent, if I want to be really specific. 1216, oh no, 12162, and then 162. Yeah, so 12.16. So why is it 12%? That's a great question. So let's look at the histogram. We're looking for the percentage of girls who ate 6 or more servings per day. So first, how many girls, straight up, just count them. How many girls ate 6 or more servings per day? Not percent, but literally how many? According to this histogram, how many ate 6 or more servings per day? 9. 3, 3, 3. The 6 column, the 7 column, the 8 column, I think that's what they were, 6, 7, and 8. There are 9 girls who ate 6 or more servings. But how many girls were asked? How many are in this study? 74. So it's 9 out of 74. And if you go to your calculator and you do 9 over 74, you'll get 12.162 bar percent.
Did you get 9 because the 6, 7, and 8 columns are like lined up with 3?
Yeah, that's exactly it. Yeah, I mean, at first you have to ask yourself, is it 2 or 3? And I kind of think it's past the midpoint, but barely past the midpoint. And it has to be a whole number because we're counting. So it looks like it's 3 to me. So a lot of people said the wrong answer there, which is fine. We're here to learn. But I'm curious where all these wrong answers came from, so we can see what not to do. I mean, I have 25, I have 30, I have 37, I have 62.6, I have 4. Where do these numbers? The 9 is for 9 students. The 9, yes. So the 9 over 74, the 9 comes from 9 students. That's correct. But if nobody wants to answer, I can't. I added 6. Okay. So that's a great mistake because there's logic behind it. The logic was wrong, so we can correct that. But it wasn't just a random answer. You at least thought about it and said, okay, I'm going to get this. So remember what the 6, 7, and 8 are referencing. They're not counts. The vertical axis is counts. The vertical axis is how many. The 6, 7, and 8 are options. They're categories almost. How many fall on this? How many fall on? Okay, wonderful. And then part D, follow-up, because it's the same basic idea, although this is not a percentage. How many of these girls ate fewer than 2 servings per day? This is not a percentage. They're not asking what percent ate fewer than 2 servings per day. They're asking what percent ate fewer than 2 servings. And remember, in the English language, fewer does not mean or equal to. Right? Fewer does not mean or equal to. So those of you who are saying 46 or so, you're including 2, right? 0, 1, and 2. But fewer than 2 would just be 0 and 1. I got 26. I got 15 for the first and 11 for the second. If you got 27, that's a judgment call. I wouldn't take off points because it's hard sometimes to see the exact scale, but I got 26. Does that make sense? Yeah, any questions on that one? Okay, so now we have one last question for chapter 1. So let's go to 1.31.
Someone asked like how you got 26.
Oh, how did I get 26? Yeah, sometimes I'm flipping back and forth between links and I don't always see the text, so thank you. Look at so first, fewer than 2 servings. Which of those columns are associated with less than 2 servings?
Zero and
0 and 1, right? Less than 2 is just 0 and 1, correct? Luis?
Yeah, I'm
Right?
listening.
So just the first 2 columns are correspond to fewer than 2. There's 15 in the first column, and there's 11 in this column for a total of 26, correct?
Yes.
Okay. So hopefully that answers that question. All right, so question 31. So you have a STEM plot of 78 7th grade students in a rural Midwestern school. I hate that word, I can never pronounce it, but in a rural Midwestern school. Is this a split stem or a regular stem plot? It is splits, right? It's two rows for 7s, 2 rows for 8s, and so on. It's a split stem plot. So, A, 4 students had low scores that might be considered outliers. Ignoring these, describe the shape, center, and spread, i.e. variability, of the remainder of the distribution. So ignoring those 4, describe the shape, center, and spread of the remainder of the distribution.
Does that mean we're just ignoring those outliers in our calculations?
Yes, you're pretending. I mean, I would even scroll up to the point, not 7 and 8, because you still want to include these 2, but I would basically scroll up to the point that you can't even see them. Or if you have it written down, cross them out or cover them or something, I think would be the best way. Right, you're still seeing my screen, right? Oh no, you're seeing my iPad. Sorry, I was never mind. I would scroll up or do something so that you're covering those four data points. And then we want to cover, so this is part A. We are looking for shape. We are looking for center. And we are looking for spread. And so let's do one at a time. Let me come back here. Okay, so remember, for shape, don't write the answer yet, but someone tell me verbally, don't write it. What are the 3 possibilities in this class for shape?
Symmetrical, skewed right, or skewed left?
Right, symmetrical, skewed left, or skewed right or skewed left. So when I say go, I want everyone to tell me what you believe the overall shape is. Doesn't gotta be perfect, but at least, approximately. So 5, 4, 3, 2, 1, go. Yes, it's very, very roughly symmetrical, approximately symmetrical, straight up symmetrical. That's all good, right? It certainly looks very symmetrical. Okay, because it's symmetrical, finding the center should be pretty easy. Okay, because it's symmetrical, finding the center should be pretty easy, at least approximately so. So 5, 4, 3, 2, 1, go. All right, so I see lots of 11s, 10.5s, 112 from Jason. That's way off. Oh, that's another typo again. 11, also with a typo. So 10 point, where did the thing go? So 10.5, why would it be 10? Okay, I can see 10.5. It's a little heavier on the left. So I certainly get 10.5, 10.5, 11. Any of those are fine. Let's make sure that we're dealing with 10s and 1s. These are IQ test scores. So, these are IQ test scores. IQ test scores are hopefully not between 7.2 and 13.6. So what's the scale of this STEM plot? What do the numbers represent here? Because 11 seems to be a pretty low IQ. This is a standard town, right? What's the average IQ in America, everyone? Nikki, you're mouthing, but I can't hear. What's the average IQ in America?
I don't know. I'm guessing 110.
110 is not the average IQ, but 100 is the average IQ. The average IQ in America is 100 by definition. So assuming these kids are not challenged, chances are that their average is not 11, but rather what would their average be?
111.
Or 110, right? The 11 are your hundreds and your tens digits. And the leaf in this case is your ones digit, right? So instead of 10.5, it will be 105. Instead of 11.0, it will be 110, and so on. So that's why it's very important when you look at a stem and leaf plot to know what the scale is. So in this case, I'll put the center, let's say, at 110. Does that make sense what I'm saying? All right, and then we have variability or spread with the latest recognition of what these numbers represents in write down the spread 5, 4, 3, 2, 1, go. So let's see, I have 86 to 136 because remember we are ignoring the first two. So yeah, 86 to 136 would be correct. Very good. Very good. Does that make sense? All right, and then we have part B, which says, we often read that hey, look at this. We often read that IQ scores for a large populations are centered at 100. What percentage of these 78 students, so now we are including the original 4, have scores above 100? So I have to count this too. Calculator. Okay. So the question is, what percentage of these students have scores above 100? So go ahead, write the answer if you have it. So I have a few at 79%. I have an 83%. I have 79.48%. So I get, and Leanne, you're going to hate me for this, but I get 79.49% because I knew to round that 8 to a 9 because the next digit is 7. But that's just me being an asshole. So why is it 79%? Because I counted 62 of the 78 to be over 100. In hindsight, I probably would have counted the other ones and then subtracted because there's a lot more over 100 than there is less than 100. But does that make sense? Any questions on that one? Yes, no, maybe. So you divided 62 by 0, 0? No, not by 100, because there weren't 100 people. How many people were there? 78. So I divided by 78.
So we're not ignoring the 4 anymore?
So we're not ignoring the 4 anymore.
Okay.
That's correct. In fact, the question specifically says, of the 78 students, right? So yes, we were not ignoring them. Where did you get 62 from again? I literally counted with my 1, 2, 3, 4, 5. I counted every leaf above 100. Starting from the first one, which was 102. Right? I had a stem of 10 and a leaf of 2. 102, 102, 103, 103, 103, 103, 104, 104. Each of those is one data point. So I counted it. Now, of course, in hindsight, I would have counted the other way. Starting with 72, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 that are not over 100. And then the remaining 62 would be over 100. Does that make sense? Yes, but no, the one who asked, I want to make sure. Yes, okay, good. Okay, so it's 5:15 and we have finished chapter 1. I covered everything I wanted to cover. I covered every problem in the workbook. But it always happens at the end of the semester to make sure that you're all prepared for the final. I end up having to rush because things certainly slow down as things get more challenging. So even though chapter 2, according to the syllabus that I was given, the recommended schedule for the course starts next week, I would like to spend a few minutes on chapter 2 now. If we can stay a little bit ahead of schedule, we'll be safer. Plus, the Tuesday, Thursday class this semester actually misses 2 class periods because we have Thanksgiving and something else. I don't even know what. So compared to the Monday, Wednesday, we have fewer classes, which means they have more chance to cover than we do. So we are going to start chapter 2 right now. Don't hate me for it. I'm just looking out for you. Well, you can hate me anyway. I really don't care. But either way, we're going to start chapter 2 right now. And chapter 2 is on describing distributions with numbers. Describing distributions with numbers. Up until now, our descriptions of distributions have been qualitative, shape, kind of like this, center. Yeah, we get a number out of it, but it's very, approximate, where do I put my finger spread? Yeah, from here to here, but there's no real math involved. It's just lowest to highest and certainly outliers. So section 2.1 is on the very first method of measuring center. Specifically, we are looking for the mean. In mathematics, there are multiple means. What we're looking for technically is called the arithmetic mean, which is a term you don't have to worry about because we're not going to look at any other types of means. But if you're ever like out there at parties and stuff and you want to show off, you can impress people with your knowledge of advanced statistics. I never get invited to parties, so I wouldn't know if this works or not, but I've heard good things. So measuring means. So given data points, x1, x2, all the way through xn, what does that stand for? Your first data points, your second data points, all the way through your nth data points, x1, x2, all the way through xn. The mean, which is denoted by x bar, that's just the notation that we use for the mean. This is your standard third grade. Oh, I took a bunch of tests. What's my average formula? How do you find your basic average when you're a kid? You want to average all your tests. What do?
Add and divide by the total number.
Exactly. You take your first, you add it to your seconds and to your third, all the way to your nth. And then you divide by n, which is how many you've had. If you're actually reading the book and you come across this symbol, this symbol here just means add the x sub i's. Has anyone here come across that notation before in a class? Summation notation, that's correct. Add the x sub i's. Okay, you don't need that notation. It's just a nice compact way of writing things instead of having the dot, dot, dot. But it's not necessary for this course. So that's the first way of measuring center, the mean. And just note, the mean agrees with the balance point notion of histograms. So in the last section, when we talked about finding the balance point, that balance point was the mean. Now, as an example, suppose you have your data points, x1 is equal to 1, x2 is equal to 2, and x3 you accidentally write to be 10. What would your x bar be in this example? Right, very small sample, only because it illustrates the point without having to write lots of numbers. But what would your x bar be in this sample? So I get a lot of 4.3s. So yes, 10 plus 2 plus 1 is 13. 13 divided by 3 is 4.3 bar, or about 4.3. And if you say, oops, I meant 1. I was wrong. I'll write oops. I accidentally typed in 10 when I meant 1. then what would X bar be now?
Would it be 1?
Oh, it wouldn't be 1. It'll be 1 plus 2 plus 1 is 4. 4 over 3. 4 over 3 is 1.3 bar. About 1.3. Agreed? So what we see is that by a large change in a value, we can significantly affect the mean. Correct? So the mean is a non-resistant measure of center. It is non-resistance, which means if you make big changes, the mean will usually change by a lot. It's a non-resistant measure of center. A resistant measure says, yeah, you want to make a change? No problem. Basically, I'm going to stay the same. But a non-resistant measure says, I can't resist it. Okay, you make a big change. I'm going to be majorly affected by this. So the mean is a non-resistant measure of center. The next type of measure, 2.2, still measuring center. But this one is called the median. The median is very, very different than the mean. Anyone know how to calculate the median of a distribution?
It's like in the center, exactly.
So if I write 1, 10, 7, would it be the 10?
You put your values in order from least to greatest.
Okay, so step 1, order your data points from least to greatest. Step 2, if you have an odd number of data points, the median, M, is which one? If you have an odd number of data points, the median, M, is which one?
It's none of them.
No, it is actually is one of them. It's the one in the middle.
It's literally the middle point.
Literally the middle point is the one smack dab in the middle. So for example, I'll erase this in a second, just a simple example. If I have my data points as 1, 10, and 7, what's the median? 7. Because you first rearrange them, 1, 7, 10, there's an odd number. The median is the one right in the middle. Right? Yes, no, maybe so? What if you have an odd number? Sorry, I just said that. What if you have an even number? If you have an even number of data points, there is none in the center, right? If I have 1, 2, 3, and 4, an even number of data points, okay, so if you have an even number of data points, average, and by average I mean your standard average the 2 in the middle. Average the 2 in the middle. Right, you add the 2 middle ones and you divide. So here's an example. Here are your data points. 1, 2, 3, and you accidentally write 1,000. What's the median?
Median is 2.
Nope. 2.5. You have an even number of data points, so you average the 2 in the middle. You take the 2 and the 3 and you average them. What's halfway between 2 and 3?
2.5.
2.5. So you say, whoops, I didn't mean 1,000. I meant 10. What's the median now?
It's still 2.5.
It still is 2.5. So what would you say? Would you say the median is a resistant measure or a non-resistant measure?
Resistant.
The median is a resistant measure of change. The median is a resistant measure of center. It is tough to change a median. It's not impossible. It's just harder. The median resists it. Yes, when it comes to medians, the first step is always put them in order. If you don't put them in order, you cannot compute the median. I mean, mentally, you can kind of jump around, but it's just so much easier to first put them in order to compute it. In fact, do we have any of our displays of data that is very, what's the word I'm looking for? That really makes it easy to calculate the middle one or to spot the middle one?
A stem plot?
Yeah, a stem plot is a wonderful way because they're already written in order. The very construction of a stem plot has them being written in order. It can't be the histogram because you lose all your data points. So you can't do it with a histogram. You can approximate it with the histogram, say, well, there's 7 in that category and 9 in this category and 4 in that category. So it's somewhere around here. But a 7 leaf plot makes it really, really, really easy to do it. Does that make sense so far? Okay. So I wanted to cover a little bit of chapter 2. I also want to update my office hours because I've decided upon my office hours. So I'm going to share my screen for a second so you can see what I'm doing. These numbers might seem weird, but I have to have a certain number of office hours. And with my schedule, I had to like find times to pack them in. So here are my office hours. On Tuesday, from 12:55 to 2 o'clock, from 3:15 to 4 o'clock, which is directly before this class, and from 5:40 to 6:30, which is directly after this class. Thursday, just after the class, 5:40 to 6:30. So the office hours are, some of them are just before and just after this class. If you can't make any of those or don't want to make any of those, but you really feel like you have to talk to me, then we can send me an email and we'll try to find a time that works for both of us. I'm free 7 days a week, assuming I'm not doing something else. So I don't mind meeting on weekends. We can jump onto a Zoom and clear up whatever confusion you have, et cetera, et cetera, et cetera. So are there any questions on what we did today?
No.
All right, so I'm going to stop recording now.